Alright, here in this video we're going to continue on 5.6, solving radical equations. And remember that the main point of this was to understand that you must isolate the radical. And the problems that we need to look at are these. Now these are going to take somewhat different approaches compared to the ones that we saw yesterday. We ended yesterday with some easy double scenarios. And these will be a little bit more involved. These are going to have a couple different unique scenarios that happen, but the overall concept of isolating the radical will still exist. So let's jump into this one. What makes this problem unique is that now it's a cube root. We'll still isolate it, which means the first step will be adding 2 onto both sides. So we still have the cube root here, and now we're equal to 12. And then to get rid of that 4, we'll divide both sides by 4. So we have the cube root of 2x plus 11 is equal to 3. Now that we have the radical isolated, we need to think about what step to take next. And it's an extension of what we saw with radicals. To get rid of a square root, we square both sides. So to get rid of a cube root, we will cube both sides. That gets these to cancel out. And when we do that, we'll have 2x plus 11 is equal to 3 cubed, being 27. And then once we reach there, we're back to a linear equation. So we'll subtract 11 from both sides. And when we divide by 2, we'll get a final answer of 8. Now, yesterday we covered that it's important to double check your answers. You will want to take this 8 back into the original setup and make sure that you get a true statement. So I'm going to do that right here. So we have 2 times 8. And we're hoping all this lands at 10. So 2 times 8 is 16, plus 11 is 27. Cube root of 27 is 3. So we have 4 times 3, which gives us 12. And then when I subtract that 2, we get a true statement that 10 is equal to 10. So 8 indeed checks out. So the only thing that was different about this problem is that you had to use cube root instead of square root. If you remember back to last chapter, we saw that indexes to the n power are the same thing as 1 over n. So really, if this problem's throwing you off, just understand that that's the 4th root of x. And we'll solve this by first isolating, dividing by 2, and we'll get that the 4th root of x is equal to 1. Similar to the last problem. To get rid of a 4th root, we're going to need to take both sides to the 4th power, and we get that x is equal to 1. And we can double check this back in the original setup. So if I have the 4th root of 1, 4th root of 1 is 1. So this is 2 times 1, which is a 2. 2 minus 2 is 0. This answer does indeed check out. So this problem is virtually the same. Just recognize that something to the 1/4 power is the same thing as it being to the 4th root. And same thing for this problem. If you think of number 12 as already being isolated, because it is, 9x minus 11 to the 1/2 power is 9x minus 11 square root. Here's what makes this problem tricky, however. When I square this side, it gives me 9x minus 11. What I'm about to write is not correct. You are not allowed to simply say x squared plus 1. X squared plus 1 is incorrect. What's really happening here with the x plus 1 squared is that it's x plus 1 multiplied by x plus 1, which if you FOIL that out, gives you this, to get x squared plus 2x plus 1, and that came from FOILing. So if I do all 4 of these terms multiplied out, we get this, and then I went ahead and combined them. This is now a quadratic situation, and if you remember back to our quadratics, we solve quadratics by getting them equal to 0. So you can see I'm going through and taking care of this. Alright, so what I've just done, because let's revisit, because this problem is definitely tricky. This is why this is featured in a separate video. Whenever we have a scenario like this, where we have something squared, we have to FOIL it out, which then turns it quadratic, right? This guy right here, he's quadratic, and we can tell because the leading term is x squared. In order to solve quadratics, we need it equal to 0. So I took steps here to get the left-hand side equal to 0. And once we land here, we're essentially back in chapter 3 and 4. You could solve this with quadratic formula. You could do it by factoring, completing the square, any of those different methods. This one is factorable, numbers that multiply together to give me a positive 12, that also add to a negative 7, are x minus 4 and x minus 3. And then also from the previous chapter, we saw that you solve by setting up each of your factors equal to 0. That's the zero product property. So for this one, I'll add 4 to both sides. For this one, I'll add 3 to both sides. And we get 2 answers here. But as you might expect, we will need to double check these. And we'll double check them by plugging them back into the original scenario. But I'm going to need to do it twice. So I've got 9 times x minus 11 is equal to x plus 1. And I need to do that not once, but twice, because we have 2 different answers that we are trying to check. I'll check the 4 first. 9 times 4 is 36. 36 minus 11 is 25. So the square root of 25 is 5, and 4 plus 1 is 5. The 4 works. Let's check the 3. 9 times 3 is 27. 27 minus 11 is 16. Square root of 16 is 4. The 3 works. This one has 2 solutions. And if you're wondering how that's possible, from a graphical standpoint, this one's been shifted, but from a graphical standpoint, square root functions look like this. And what we had it set equal to here initially was linear, a line. And it's certainly possible to draw a line that crosses this guy 2 times. You won't be able to get 3, but you can get 2. So if you were to graph this and look at it graphically, these things would be all shifted around, but to an extent, you would see a picture that had something like this occur, where the line cuts through the curve twice, giving us these 2 answers. So there's 3 different cases that we had not seen yesterday. We had a cube root, a fourth root, a scenario where we had to FOIL, because when we squared a side, it turned into a FOIL problem. And those are all different types of solving radical equations. This one here is similar to the one that we just did. The first step is to get the radical isolated, and I'd do that by adding 5 to both sides. And you might already be recognizing when I go to square both sides, this is going to be another one of those situations that turns quadratic, because I must FOIL this. And if you write it out twice and you FOIL, you will get x squared plus 10x plus 25. Now to solve a quadratic, we want it set up equal to 0. So we'll get x squared plus 9x plus 18. It's quadratic, so you will attempt to factor it or use quadratic formula. Factoring is going to be much faster. Numbers that multiply together to give me 18, that also add up to 9 are 6 and 3. When you set both of these up equal to 0, you'd get that x is equal to negative 6 and x is equal to negative 3. Remember, you get that by taking both factors and setting them up equal to 0. And then when you solve, you get the answers right here. But we need to double check them both. So I'm going to rewrite the original equation 2 times to make sure that it works for both solutions. And I'll check the negative 6 first. Negative 6 plus 7 is 1, square root of 1 is 1. Right away, I get one of these is not going to work. Negative 4 is not equal to negative 6. That means our negative 6 is extraneous. He doesn't work. Let's check the negative 3. Negative 3 plus 7 is 4. Square root of 4 is 2. 2 minus 5 is negative 3. So the negative 3 works. Our only solution here is negative 3. But be on the lookout, because these will turn quadratic sometimes whenever you're forced to square a term like x plus 5, or to square a term like x plus 1. The final type is something like this, and we'll spend the remaining time on it. This is the hardest double scenario. The goal is to isolate a radical, and on this one I'm not able to isolate them both at the same time. So I'm going to have to take turns. I'm going to go ahead and isolate my big one on the left, square both sides. But what makes this problem tricky is that now when I go to square this left-hand side, I'm going to be foiling with some square roots. Square root of x times square root of x is actually just x. Right, we learned that last chapter. So square root of x times square root of x is x. Square root of x times 1 is square root of x. Another 1 times the square root of x is square root of x. 1 times 1 is 1. So now this left-hand side has turned into x plus 2 square root of x plus 1. And what we will do here is attempt to now get this square root isolated. So I'll do that by subtracting x and subtracting 1 from both sides. Dividing both sides by 2. So we'll now have x over 2 is equal to square root of x. Now that I've got the other square root piece isolated, it's his turn to get squared. And you can think of this as a 1x. So x over 2 squared is really x over 2 times x over 2. So I'll get an x squared over 4 is equal to x. And you might be wondering, well, how can I solve this, Mr. Cottle? This looks a little strange. I've got a fraction. I know it's quadratic, but I'm not ready to factor it. Well, I want to get the x squared, by himself. So I'm going to multiply both sides by 4 to get that x squared is equal to 4x. This is quadratic, so I need it equal to 0. So I'll subtract 4x from both sides. It's now quadratic with a GCF. So one of our potential answers is 0, and the other potential answer is 4. So you'll want to plug both of these back in. I'll pause the video and then double check them here to reveal to you because I'm running out of time. Let's double check these two answers into the original setup. When you go to double check these, the 0 does not work. We get square root of 3 is equal to 1, which is not true. However, when we check x is equal to 4, I get square root of 9 minus square root of 4. 3 minus 2, 1 is equal to 1, which means that for this final problem, x is equal to 4 works. Rewatch this problem again if you need assistance.